Good afternoon, everybody. We are going to have this course on durability of concrete structures. It's planned for a 6-hour lecture. So we'll have a couple of breaks in between to clear the doubts which you may have. So the course is divided into 3 parts. Part 1 on looking at the corrosion of the steel itself in which is embedded in the concrete, and part 2 is looking at how the concrete deteriorates, and then part 3 is understanding these mechanisms, how the steel corrodes and how the concrete deteriorates, what we can do to prevent such deterioration in the concrete structures, or rather we call it durability based design. So, so we are getting into the part 1, which is on corrosion of steel reinforcement. Remember, we will look only at the steel, how the steel corrodes and what is the why the steel is corroding. So this is the outline for the part 1, which we will first cover why do we really have to worry about corrosion, or what is the significance of the corrosion, and then we will go into the various mechanisms of corrosion in reinforced concrete structures, in which we will cover 2 major deterioration mechanisms, which is chloride induced corrosion and the carbonation induced corrosion, and we will also cover some other reasons by which steel in the concrete can corrode, and then we will look at different types of reinforcement which are used in the concrete, which is the conventional reinforcement and some of the advanced steels which we have, but we will also cover some drawbacks of those advanced steels also. And then we will look at how to prevent corrosion or how to mitigate the corrosion. Let us say some structure is already existing and it is some 20-25 years old structures. Then on such structures, how can we stop corrosion if it is happening? And then we will at the end we will look at the couple of methods on how to monitor the corrosion. In other words, how to assess whether the corrosion is happening or not, and also if it is happening, fast the rate of the corrosion is. So we will look at these aspects. So first let us go into the significance of the corrosion. Before getting into that, we will see also the durability of what is durability. When we talk about durability of concrete structures, the course title itself is durability of concrete structures. So first we need to know what do we mean by durability, or durability of cement concrete is defined as its ability, the concrete's ability to resist the weathering action, chemical attack, abrasion or any other process of deterioration. Like in this course we will focus more on the corrosion as a attack, and what can the deterioration, it can be a result of chemical reaction or physical deterioration within or on the surface of the concrete. Again, when we talk about the corrosion, what is happening is deterioration or something is getting into the concrete which leads to the corrosion of the steel which is embedded inside the concrete. Okay, so and corrosion of the reinforcing steel is considered to be one of the most common deterioration mechanisms. So that is why we are going to focus more on that the mechanism in part 1. Like the chemical attack, abrasion, all that will be covered into the part 2 of this course, and I am going to show some examples on where corrosion actually happens, or So this is a picture where you can see actually there is a ship which hit the column of this bridge which is in USA, Tampa in Florida. So what happened is accidentally this ship hit the bridge pillar, and then they had to put a new bridge over there. So this is the new bridge which was constructed right next to this old bridge location, but looks very nice bridge, and this bridge has received several international awards for design. However, in about 13 years after the construction of this bridge, we found that the steel tendons which is inside these pillars were actually corroding very heavily, and just in 13 years you can see the third picture in this slide, it's completely corroded. I mean it's not at all acceptable for a bridge of this nature. Okay, So failure or corrosion at this level for in 13 years is not really acceptable. So we have to really design our concrete structures so that these kind of things does not happen. When we design some kind of bridges or anything, we will normally think like it has to be 50 years or 100 years or 150 years depending on the requirement, and we found that the corrosion, premature corrosion can happen. So that's what we have to prevent. So if we want to prevent, we have to really see what are the mechanisms which is happening. So another example is Golden Gate Bridge. We all, it's whenever we look at this bridge, we think about USA, or it's a landmark structure. When you look from far away, you don't see much problem, and the picture on the right side shows like somebody is actually applying coating on the steel cables over here. So it needs regular maintenance. But when you look at the steel trusses over there, you can see a significant amount of corrosion here. And if you look at the concrete elements of this bridge, there also you have significant amount of corrosion. So even though the structure looks very good and nice from far away, when you go closer, you see that a lot of issues are there on these structures. Another example is in Canada. Again, it's an old bridge. And here what we can see is this bridge also experienced severe corrosion because of the chlorides, the de-icing salt, which they put on this bridge during the winter. And actually the inside, there were also cases where inside this girders and these girders, there's a lot of water gets in during the winter, rainy season, and then it just settles there. And also we get a lot of chlorides during the winter. They put chloride on this bridge so that you can actually drive during the winter, because it's too cold, and then ice starts forming on the concrete surface. So to melt those ice, then they put chlorides. Anyway, the problem is that chloride slowly penetrates into the concrete and it then corrodes the steel. So why I'm showing all these examples, which are mainly on the developed countries, US and Canada, they also have faced all these problems. So this is the importance of this discussion on showing examples in the developed country, where they have faced the problem in the past and then they learn from those mistakes, and now they are actually building very durable structures. So in India today we are going through a construction boom. So we have to take these lessons which they learned from their old examples, and we must incorporate that in our current construction. If we do not do that, then we will have a significant repair exercises in the future, which will be very expensive, and we want to avoid that. Now this is a pie chart which shows distribution of corrosion cost of corrosion due to transportation and infrastructure, government sector, and then production and manufacturing sector, and then utilities. So what you see here is, in this utilities, a lot of pipelines which are also made out of concrete structures are there. In infrastructure you have a lot of bridges, building and all that. So these majority of these structures have concrete elements in this. So controlling corrosion in concrete is very much important to reduce this cost of corrosion. And how much is this cost of corrosion for India? In 2012, it was reported that the direct cost of corrosion was 2 lakh crores per year. It's not a small amount, 2 lakh of crores per year. So you can imagine how many zeros you want to put after this 2. So we have to really work on how to reduce this cost. So we need a corrosion protection strategy to minimize the repair and maintenance cost. And here, I don't have those points here, but I'll give some indication on this 2 lakh crores per year, what it really means. It's about 3 to 4% of our country's GDP, which is too much. That money should be invested on actually controlling or building new infrastructure rather than putting on controlling the corrosion or repairing these structures. So we really have to work on building durable structures so that we can reduce the cost of corrosion which we incur today. Okay, now let's get into the corrosion mechanism. So before we talk about the corrosion mechanism, First, let's see why iron actually corrode. First of all, so iron is actually, we get the iron ore, so we make steel from this. We get the iron ore and then we put that iron ore into a blast furnace and then melt it, and then what we do after that is roll that material or the steel to make it into a particular shape. So if you are talking about a rebar, you have to roll it through a mill which makes the rebar, and then you get that deformed shape on that. Then we take the rebar and put it in our concrete structures, which is then exposed to moisture through rain, high temperature because of sun, and also chloride. If we have a lot of structures along the coastline, so we have a lot of chloride there, and also, I mean, I don't have that picture here, but carbon dioxide also is another factor or another exposure condition which we have. So what happens is, from here, from the iron ore, as you do these processes, it's actually taking a lot of energy, both thermal and mechanical energy. So when we heat it up, it's actually energy level increases because of the heat, and when you roll it, you're actually using the mechanical energy. So eventually the steel, after the rolling mill, the steel will have a higher energy level than the iron ore. Now there is a tendency that if the steel has the higher energy level, there will be automatically a tendency for that steel to go back to its original energy level. So during this exposure, when we put the steel in the concrete, it exposed to this moisture, temperature, chlorides, all that, and it will try to go back to its original energy level. And how does it go back to the original energy level is basically the corrosion mechanism. So here are a couple of equations through which the corrosion reactions can happen like this. In presence of oxygen and moisture, corrosion can happen. And so you see here this Fe2O3, this is very similar to the composition of the iron ore. So this iron ore you take, make the steel out of it, and then steel goes back to its iron ore or that composition, and that is what is corrosion. So we can even define corrosion as extractive metallurgy in reverse direction. So this can happen. The only point is, if you have a very good steel and very inert environment, then this rate of reverse process is very low, or the rate of corrosion is very low. If you are having a very aggressive condition and not a good quality steel or something, then you can have a very large or a high rate of corrosion. Now looking into the concrete, what is actually concrete? I mean, I know you might have already taken classes on concrete technology, but still let me just brief it. And in concrete you have CSH, which is the main binder, calcium silicate hydrate, and then you also have a lot of hydroxides in the concrete. So these hydroxides contribute to the large or high pH which the concrete pore solution has. So if you look in this scale, pH scale, you will see that the concrete pH will be more towards the right end or highly alkaline in nature. That's the pH of the pore solution in the concrete, and this is exactly one of the reason why we are able to use steel in concrete, because the steel is very well protected in this high pH environment. So, and if you are talking about the steel, yes, steel is also, we think steel is very homogeneous material, yes, in terms of concrete, yes, but when you look in a microscope, steel also has different phases in it, and this picture here is actually about 0.1 by 0.1 millimeter size. So you can see how small an image, and you have different phases in this. So if there is corrosion happening, it can initiate at one of these grain boundaries, or even in one of these phases might be more vulnerable to corrosion than the other. So you can have corrosion in steel also. I mean, this is one of the reason why steel gets corroded also. Now when we talk about steel embedded in uncontaminated concrete, we normally don't see corrosion, because if you have a lot of structures which are still standing, reinforced concrete structures which are still standing, but there is no corrosion. You can even see structures which are 40-50-year-old, but there is no corrosion on those structures. So there is a reason why there is no corrosion on those structures. The reason is, like I mentioned earlier, when the steel is exposed to a very high pH condition, that is our concrete. Concrete has very high pH. When it is exposed to high pH, steel is very well protected and it does not corrode. Now, the moment you put the steel in concrete, it first reacts with the immediate pore solution or immediate cement available, and it forms a very thin layer which we call protective layer or passive film around the steel surface or on the steel surface. And this layer has a peculiar feature which is very thin and it is invisible, we cannot really see that layer, and it is very stable and dense. So, because of this peculiar feature of this passive film, it protects the further steel from corroding. Like if you are thinking about a copper plate, you can see, remember this green coating which is formed on the plate, and that is nothing but the initial oxide layers. So, like that, and that layer protects further the metal beneath that from corrosion. Similarly, in the case of steel, you had this oxide layer, iron oxide or hydroxides, which is formed, which protects it from further corrosion. So, we call this layer passive layer or passive film, protective film, different names are there. However, corrosion can occur when exposed to aggressive conditions. What basically happens is, this passive film which we said, it will actually get damaged or it will be broken by these aggressive elements. So, before getting into how that is happening, we will look at what are the essential parts of a corrosion cell. Now, you have electrolyte, over here the yellow region is the electrolyte, and then you have this gray region which is the metal. And in the metal you can see one region is anode, which is the region where there is metal loss, and the cathode is the adjacent region which is actually assisting the anode or in corroding. So, you might have seen rebars where only some portions are corroded, some are not corroded. So, this region which is actually corroding, we call it anode, the region which is assisting in corrosion, we call it cathode, and there is a ionic conduction here. So, through the concrete you have a very, you can have these ions moving, which is hydroxide ions mainly. We will show that in the next image, and then you have this electronic conduction through the metal itself. So, these four components form a corrosion cell. So, you have anode, cathode, and an ionic conductor and an electronic conductor. Okay. Now, what are the typical half cell reactions which can happen at the anode and at the cathode? So, at the anode what happens is the ion dissolves into Fe2 plus and 2 electrons, and at the cathodic side these 2 electrons will get consumed. So, where is this happening? This is happening here in this anodic region. Ion becomes Fe2 plus and 2 electrons. These 2 electrons move, or the charge is transferred to the cathodic side where it is absorbed, and in presence of moisture and oxygen you have hydroxide ions forming. Okay. Now, this is an example where you can see a lot of corrosion where the just above that water level or at the water level, you can say there is a lot of corrosion here. You can see this, below this there was a lot of water. So, what is happening is the region where you have this wetting and drying. So, this region we can say of this pillar we can say it is wetting and drying is happening. So, because of this wetting and drying, this region is much more vulnerable to corrosion, and you have both enough moisture and enough oxygen available in this region. If you go to the top of this pillar, you might find that the amount of moisture might be relatively less. If you go very deep on this pillar, you will see way below the water level or inside the water body, you can see that there is limited oxygen available. So, where there is enough oxygen and moisture available, you will see that maximum corrosion will happen in that region. So, we always worry about this wet dry region, or we sometimes call splash zone. So, that is the region where you will see maximum corrosion. Now, just the same equations, I am putting this in a little bit different perspective, where you can see the anodic side, or you can see this region the steel is actually embedded in the water, and this region you can see it metal is lost, and you have this Fe2 plus ion getting into the water or dissolving into the water, coming out of the steel rebar, and then you have these 2 electrons which are released, and that electron is moving towards the cathodic side, either to the right or to the left. This is the cathodic side, where you have these 2 electrons being absorbed in presence of moisture and oxygen, which is forming the hydroxide ions, and this hydroxide ion is moving towards the anodic side, and this Fe2 plus is already available. These two combine to form iron hydroxide. Okay, so that is what is rust. So, and you can notice anode and cathode coexist on the same piece of metal. That means same rebar, you have both this anodic location, and in the same rebar you have a cathodic location. So these two are actually the complete cell is formed, or the 2 half cells are formed, and then you have this electrochemical reaction going on. Now, 2 major types of corrosion in concrete structures. You have one is carbonation induced corrosion, and the other one is chloride induced corrosion. If you are in a coastal region, chloride induced corrosion is the mechanism which we really have to worry about. If you are talking about an inland region where you don't have much chlorides, but you have a lot of carbon dioxide available, then and relatively dry environment, then you have carbonation induced corrosion. That's the governing mechanism. What's the difference between these two? One is, in the carbonation induced corrosion, you might see more or less a uniform pattern of corrosion, where this region here is the corroded part, and this is the base metal which is not corroded yet. So you can see the difference. It's more or less uniform. In the case of chloride induced corrosion, instead of a uniform corrosion, you are actually seeing a pit being formed, and pitting corrosion. This is very peculiar feature of the chloride induced corrosion, and this is one of the reason why we are really worried about it, because when you actually inspect a bar, you can actually see that there are some regions where the pit is formed. So if you take the cross sectional area, this region is only what is available for resisting the stresses. So that region will have a higher stress, and then structure can fail faster. So going into the carbonation induced corrosion, what's really happening? So this carbon dioxide in presence of moisture will form carbonic acid, and then this carbonic acid will actually combine with the calcium hydroxide which is present in the concrete to form calcium carbonate, which is the white patches which you might have seen on many concrete surfaces. The white patch you will see, and this white patch will actually leach out. Then at the higher level of carbonation, you can also see that the calcium silicate hydrate, which is the binder in the concrete, that will liberate the calcium oxide, which will again get carbonated, or you will see more calcium carbonate being formed. And the end effect of all this is that it reduces the pH, because in these reactions the calcium hydroxide is consumed. So when you say hydroxide is consumed, your pH level is going to decrease. So the end reaction is given here, calcium hydroxide plus carbon dioxide forming calcium carbonate and moisture or water. So this is being consumed. Calcium hydroxide is one of the reactant, and as it is consumed, hydroxide concentration is going to decrease, or in other words, you will have a lower pH, or the pH is reduced. Now when the pH is reduced, our steel will not be protected against corrosion, and that is the reason why we are worried about the carbonation. So we have to make our concrete so impermeable that the carbon dioxide will not penetrate into the concrete, or it will take much longer than our design life for the carbon dioxide to reach the steel surface, or the surface of the steel which is embedded inside the concrete. So just to make it more clear, carbon dioxide is penetrating through the cover concrete. It reacts with the calcium hydroxide forming calcium carbonate and moisture. Now this is being consumed, which results in the reduction in the pH, and when the pH is low, steel starts corroding. Okay. Now the other mechanism we were talking about is chloride induced corrosion. So in here again chlorides are penetrating through the cover concrete, it reaches the steel reinforcement, and earlier I mentioned there is something which is called the passive film which is formed on the steel surface, that is this green layer is what is that passive film. Now what you notice here is these chlorides are attacking in some region on the passive film, or you have a localized attack. So here this portion of the passive film is broken, here this portion of the passive film is broken. So this is the local attack. Now as this localized attack keeps on growing or keeps on continuing, you see that significant amount of steel is lost, but only in some point on the steel. For example, if you are inspecting here, you will not see any corrosion happening. That's the challenge associated with the chloride induced corrosion, is to find out actually what is the effective cross sectional loss. So if you look here, there is no corrosion, but if you look here, there is almost 50% of the steel is lost. So that's very challenging to find where the pits are actually growing, and then really understanding what is the resulting or the residual steel which is available. Now this is again same in the chloride induced corrosion. What is happening in the chloride induced corrosion, like we said earlier, you have an anode where the iron Fe becomes Fe2 plus and 2 electrons are released, which goes into the, or this charge is being transferred to the cathodic side. And when you have sufficient amount of chloride in the solution or in the concrete pore solution, that chloride will combine with this. So this is the chloride available, that will get that will be combined with this Fe2 plus which is released from here, that will form FeCl2, which in the presence of moisture will form HCl and some rust. So this is the rust being formed. Now this HCl will precipitate again into H plus and Cl minus. So the same Cl minus which was used in this equation, and it is again reacting with another set of Fe2 plus ions, which will form more FeCl2 and which will again form more HCl and more rust, FeOH twice. So this reaction is a catalytic reaction, and then it keeps on going on until you have, or in other words, if sufficient chloride is present, and then it is very difficult to stop corrosion unless you can get rid of, completely dry the system so that it cannot continue. But as long as there is some moisture and oxygen available, it will continue to corrode, and that's a challenge. And so we have to ensure that again our concrete cover is highly permeable, so that it takes long time for, or either rather prevents the chlorides from entering in and reaching the embedded steel. So again it all boils down to how good a concrete cover you have in your structures. Okay. Now when you talk about I said, like, you have to actually prevent the chlorides from entering the concrete and reaching the steel and building up some concentration at which the steel will start corrode. Now that is that minimum amount of chlorides required for initiating corrosion. We call that chloride threshold. So it's critical chloride threshold, which is the minimum amount of chloride threshold, which is minimum amount of chlorides required to initiate corrosion. Now for example, with the first two these two steels, these are the conventional steel which we use, and these are some of the this is a corrosion resistant steel, this is a stainless steel rebar, this is another different better grade stainless steel rebar. So you can see two stainless steel rebars, one of the corrosion resistant rebar and two conventional steel. You can clearly see that if you use this corrosion resistant or the stainless steel 304 rebars, you can actually increase the chloride threshold. In other words, the amount of chlorides to initiate corrosion is much more than these two cases. If you use this steel, the amount of chloride required to initiate corrosion is more than the case, or the amount of chloride required for initiating corrosion on these two. So the idea is to use a steel rebar which has a higher chloride threshold. So for the same concrete, if you use a steel rebar, or if you put a steel rebar with a higher chloride threshold, eventually it will take more time for the chlorides to reach the steel and build enough chlorides to initiate corrosion. So that way we can enhance the life of the concrete structure. That's why idea is to use a steel rebar which has higher chloride threshold, or do something to the concrete or to the steel so that you can actually increase the chloride threshold. How we do that is either by applying some coating on the steel or by mixing something in the concrete which can actually increase the chloride threshold. We will cover those two topics later, but let us see what is the chloride threshold, and these are typical locations where you can actually experience chloride induced corrosion. This is actually looks like a palm tree, but this is actually a reinforced concrete pile. You can see the rebars here, this is the circular stirrup here, and where this is corroding, it's right above this water level or right at the water level. You see much more corrosion because that is a region where both oxygen and moisture are available in enough quantity, and it accelerates corrosion there. Now here this is a bridge, again here another bridge. This is the bottom view of this bridge where you can see significant amount of corrosion, and at the bottom side where you have actually more moisture than the top surface. So whenever you look on drive on a bridge, you can see if there is any corrosion at the bottom of the bridge, because most of the time when you drive you will not notice what is at the bottom side of the bridge. So this is where we have to really worry about, and you have to maintain this entire elements in good condition. This is again another one where there is some protection already in place, some jacketing has been done or some protection has been given where the wetting and drying is could have been happening. So here you are not much worried compared to this location where just above the water body. Now this is another one. This building is actually facing the sea, and you can see significant amount of corrosion. You can see here it's corroding all these balcony. It's a lot of corrosion is happening on the balcony, and here is a close up of this thing. So here the chlorides are actually airborne chlorides are being carried, and it is actually sitting or getting deposited on the concrete surface, and eventually that will diffuse into the concrete through the cover concrete and reach the steel. So first these airborne chlorides will come and get deposited on the surface of the concrete, and once it is deposited on the surface, very slowly it will penetrate through the cover concrete and reach the steel rebars. And then once enough chlorides are there at the rebar surface, it will start. Now there is one more mechanism which is stress induced corrosion, and this is actually one of the issue which we may face in pre-stressed concrete structures, because we have the steel cables which are under stress in pre-stressed concrete, and that may have, if you apply too much of stress, you may have problem like that. So we have to be careful in not over stressing the steel, okay, and it results as a in a combined action of both tensile stress and if you have aggressive environment or a corrosive environment. So both stress and corrosive environment, so the rate of reaction or it might be much more vulnerable than a case where there is only corrosive environment, the metal is not experiencing any pre-stress. Now post tensioning strands and then welded joints, you can have corrosion. I will show the picture here. This is on the welded joint. You can see there is a heat affected zone right outside this welded region. This portion you can see a crack here, and here also you can see a crack here. This is because of this is the heat affected zone within that region itself, right adjacent to the weld. So if you look very closer, you don't really see what the corrosion is happening or progressing into the metal, and when you look from the surface you may not notice that problem. So here you can see a cross section view, you can see this fine cracks here, and it's actually corrosion growth into the metal through the grain boundaries. It's actually the transgranular cracks, it's actually growing through the grain boundaries. So this is a important phenomenon to be considered when we talk about the pre-stress concrete structures. Now another form of corrosion is galvanic corrosion, where, or we also call dissimilar, when two dissimilar metals are in contact, it leads to corrosion, which is called galvanic corrosion. On the picture here you can very clearly see that this nut is not having much corrosion, but the bolt is severely corroding, and this metal, the base, is also corroding significantly. So why it is corroding? Because this nut is of different metal than this. So we should try to, and this might accelerate the corrosion. If you don't have dissimilar metal, or if both the nut, bolt and the metal which is connected, or the base plate, if all of these have same metal or are made of same metal, then you may not see this galvanic corrosion coming into the picture. There may be other forms of corrosion, but galvanic corrosion can be eliminated if you use same metal. Now how do we distinguish, how do we find out whether we can use two metals, or whether there will be a galvanic corrosion or not? So this is a table which we can see, and if you go in the top of this table, you see more noble materials. As you go bottom to the bottom of the table, you see more and more active material, or the materials which can corrode very easily. So for example, you have this magnesium here, zinc here. The zinc is also used, magnesium. So these things can corrode faster than the or they are more vulnerable to corrosion than the steel. So if you put a steel and connect that to zinc, you will have preferential corrosion of zinc. So that's the idea of galvanizing galvanized steel. Actually you put zinc coating on the steel, so we actually expect the zinc to corrode and not the steel to corrode. So this is the reason why we actually go for galvanized iron. Anyway, the point is you should not connect any two of the metals in this table which are very far apart. So if they are very closely placed on this table, then there may not be significant galvanic corrosion. The further the distance between the two metals in this table, you might see that the chances of galvanic corrosion is more. Now corrosion due to crevice corrosion. So here you have difference in the oxygen availability. Like if you look in the equations which we discussed earlier, the cathodic equation, you have oxygen is a must, and in the anodic reaction there is no oxygen involved, but in the cathodic reaction oxygen is involved, and you need oxygen to continue the corrosion. So what is happening here is, in the beginning, imagine this is a washer, on a bolt nut system, this is a washer and this is the plate, and you have this washer, and initially there will be some oxygen available underneath the washer. Once that is consumed, there will be a reduction in the concentration of oxygen in this region, or oxygen depletion can happen, and because of that reduction in the oxygen depletion, this region will, after that point, this region will start functioning as an anode, and this region will assist the corrosion, or it will start functioning like a cathode, because you have a good electrical connection here, and then sufficient moisture in the ambient environment, so that you get enough ionic conduction also. So you can generate a battery here, or a corrosion cell here, where the area below the washer, it functions like an anode, an area away from that functions like a cathode. And why it is functioning like an anode is because of the depletion of the oxygen concentration over here. We have seen that once the steel in the concrete starts corroding, you have significant cracking happening in the concrete structures. Now why this cracking happens, and is it actually good that it is cracking? There are multiple views on this. So why this cracking happens is because there is a significant increase in the volume of the rust products or the corrosion products when compared to the volume of the bare metal, okay, uncorroded steel. So for example, when steel corrodes, its volume increases by approximately 6 times. So 6 times if the volume is increasing, it's going to exert tremendous expansive pressure or expansive stresses in the concrete. So here you have the steel which is corroded and this much extra rust, I mean the rust is forming and it is occupying a lot of space around that steel, and which is creating this expansive stresses. If because of this expansive stresses, the concrete cover can crack. So that is why corrosion induced crack can happen, or cracking in concrete can happen because of the expansive nature of this rust. Now, is it good? In one way, if you look at, it is good that it leads to some crack, and then so that we can actually see that something is actually wrong. But on the other hand, we can also think, if this crack is not there, then it will take longer for that steel to corrode. So you have to judge on that. So but point here is that it can lead to cracking, and one way it is for an inspector, this rust stains will come through these cracks and pores in the concrete. It can then we will see these brown stains on the surface. Then we get a warning that something wrong is going on inside, or some corrosion is happening inside. So you get enough time to either repair that structure or do something about it. Okay, we will actually go through, we have some questions here. We'll actually clear those doubts before going further on the lecture, and then at the end, if time allows, we will actually clear whatever the remaining questions which you have. So let's take few minutes in answering these. The first question which came out was how can the pH value of concrete be determined? We have something, you might have used the phenolphthalein indicator in your chemistry labs. So this phenolphthalein indicator, we can actually use it for determining whether the pH is high or low in the concrete. Cannot the exact pH value. For that there is another test method which we don't need to cover in this basic course. So the we can take a concrete piece and spray this phenolphthalein on the surface of the concrete. If depending on the color of that surface, we can, this test method will be covered in the next lecture. So I am not going to go deeper into that. So but only the main idea is we can use phenolphthalein indicator to check the pH of the concrete. Next question. The next question was and how the pH will be maintained during construction. The pH will be maintained because the idea is, if there is no carbonation happening, there will be no change in the pH. So if we can make the concrete very good that there is no carbonation, or there is no very low permeable concrete, so that the carbonation is very low, then pH can be actually maintained. Okay, now how will be the chloride? It's not chlorine, it's chloride be penetrated into the concrete when the concrete is waterproof. So the amount of the pores which we are talking in concrete is very fine pores, and when we say the chloride is penetrating into the concrete, we are not talking about something which happens in few minutes or few weeks or few months. We are talking about years and decades. So it's a very slow process, and chloride, the concrete, if it is having some pores in it, chlorides will actually penetrate through the concrete in very slow diffusion process. Okay, so it's not something which we are talking like something which happens very short period of time, and even though it is waterproofed, there will be time when the chlorides will find a way to go through this concrete with pores. So it can actually happen, but only thing is, it may not happen in 1 year or 2 years. It might happen over a period of time, which is maybe even in decades. Next question is, why will the different types of metal used in the concrete, what is their use? So depending on different types of metals, we use mostly steel, but with some modification of the steel. Like for example, if you want a high strength steel, you will go for steel which has higher strength. If you are talking about highly ductile steel reinforcement, then you will go for some kind of TMT rebar which has a, so depending on the properties which we need, and if you are looking for a corrosion resistant steel, then we will go for stainless steel, but very rarely we use stainless steel. But that's the idea, like depending on what type of properties are you are looking for, accordingly you have to choose the steel. Why will corrosion happen when there is unavailability of oxygen on the surface of steel inside the concrete? This is again actually there is enough, if your concrete is exposed to atmospheric conditions, you can have enough oxygen available at the steel surface inside the concrete, or at the surface of the steel embedded inside the concrete. So, and that much amount of oxygen is sufficient to sustain the corrosion reactions. Okay, so you don't need a lot of oxygen, but pores will actually there are enough pores in concrete which will lead to the penetration of the oxygen or diffusion of the oxygen into the concrete and be available at the steel surface for the corrosion to occur. Why are steel, I suspect this is steel rebar. So why are the steel rebar used in the concrete structures? Concrete is very weak in tension, steel is very good in tension. So we use these two properties of steel and concrete and make this composite structure, where both steel and concretes are used. Wherever you need resistance against tensile stresses, you put steel, and where you need resistance against compression stress, you put the concrete. And that's how we design concrete. I think that's clear. Can we use can we use nickel titanium bars for the seismic retrofitting? Yes, we can use, but it will be very expensive, so we may not eventually use. But technically speaking, yes, maybe it is possible. But what type of corrosion will lead to the structure quick failure? Lead to the quick failure of a structure. If the structure is over reinforced, then you can actually see that concrete portion will fail. And here your question is, I think, what type of corrosion will lead to quick failure of structure? Mostly chloride induced corrosion, or if there is stress induced corrosion, which we cannot actually check. So we will have relatively quicker failure in such scenarios. Does the selection of aggregate affect on durability of concrete? Yes, it does affect the durability of the concrete. Selection of aggregate can definitely affect. If you have a very bad quality concrete, then bad quality aggregate, it might lead to cracks in the concrete and many other issues. So the discussion on that is more appropriate for the part 2. We will cover that also. Then the next question, how can we decide the cathodic or anodic part in a steel rebar? So this one I mentioned that you can have the cathode and anode on the same steel rebar. However, this is very dynamic process. So it's not that we are fixing an anode location and fixing a cathode location. What we have, it's a very dynamic process. So right now, if one location is anode and another one is cathode, you come back after some time, you will see that it's actually anode is moved from there. So it's a very dynamic process. So we don't really fix them. But if you want an answer why some region is anodic, it's mainly where there is either a grain boundary or some vulnerable, some phase of the steel which is more vulnerable, then you can have a corrosion starting at that location. And if you are talking about the cementitious system also, if there is an aggregate or there is a small pore at the steel surface, or if it is near the ribs of the steel, these are the locations where corrosion can initiate at an early time, or some defects on the because of the geometry. There are many reasons for this to happen, but the point is it's not fixed. It keeps moving. It's a dynamic nature. So you don't have a fixed anode and a fixed cathode on a rebar. Now, why carbonation of concrete can lead to corrosion of steel embedded in concrete? So when you say carbonation of concrete, the concrete gets carbonated and it reduces the pH of the pore solution or the pH of the concrete which is very next to the steel rebar at the surface of the steel. When the pH is reduced, then the steel is no longer protected, so it starts corroding. I think that's the answer for that. Better substitutes for steel which are economical. I think at this time steel is probably the most economical rebar. There are other products, fiber reinforced concrete, and then advanced type of coatings for the steel and all that, but still mostly I think steel is the most economical material to be used, and that's why industry is using that in almost all the construction sites. So this is where we stopped. Why steel corrosion causes cracking in concrete? We said that steel actually when corrodes, it expands by about 6 times, and which creates a lot of expansive pressure on the concrete cover, and which even because of this expansive stresses, and concrete is weak in tension, so it leads to cracking. Before going further, I would say, like, we will if you have doubts, you keep typing the questions, so that before the end of the session we can clear those doubts today itself. Okay. Now, common types of rebars which are used: plain or ribbed hot rolled mild steel bars. Why these ribs are used? Ribs are there because it helps in giving proper bond between the steel and the concrete, mechanical bond. Now, then you had also cold twisted deformed bars, which are not much used in today's construction, but just for the purpose of completion I have put this term here, which are again similar. It has a high yield strength because it is actually cold formed or the strain hardened steel, so that the yield strength is more with the same chemical composition. Okay. And this was heavily used in the industry a couple of decades ago, but then what we found is, because of the strain hardening, there is a lot of residual stress at the surface of the steel, and because of that residual stress, it was more vulnerable to corrosion. So people found that actually using this type of CTD rebars, concrete structures were corroding faster than other type of steel which were in use at that time. So they slowly switched to a new type of steel called thermomechanically treated, or TMT rebars. The correct technical term for this is quenched and self-tempered steel, that is QST, that is quenched and self-tempered. We will see later how that bar is produced and what are the issues associated with those bars also. And they also have a very hard surface and a ductile core. This is widely used for especially for earthquake resistant design, where you actually design a ductile structure. So you need much more elongation of the bar. So then we also have corrosion resistant TMT bars. So these are very small quantity of copper and chromium is introduced into the bar, and a little bit of phosphorus is also there, and then that is why they get this high corrosion resistance. And then we have also galvanized rebar, which is actually a steel rebar coated with zinc, and then we have epoxy coated rebar, where the steel rebar is coated with a very hard epoxy coating, and then we also have stainless steel and then pre-stressing strands. So these are different type of steel reinforcement which are used in concrete structures. Depending on what is your requirement, you will have to choose one of these and use. Mostly in India today we use this TMT steel rebars in most of our construction. So we will go to that first. So in the thermomechanically treated or quenched and self-tempered, QST. So if you go, if you talk to anybody outside Indian border, then you will see that the term QST is more familiar and not the word TMT. So TMT is a Indian jargon, so you have to go for this QST. How is this made? So you have this here, look here on this time log scale, and then you have temperature. So what you do is, when the steel is being manufactured, you actually put the steel through a quenching process. So you quench the steel in about 1 second, so 0 second, 1 second here. You reduce the temperature from 1000 degrees to around 200 degrees, and then allow the steel to slowly cool. So in this process, what is happening is slowly come to the normal temperature, or we call it tempering. It's not cooling, it's actually getting heated up again. So the heat from the core is radiating outwards. So when you do this quenching process, the surface of the steel, as you see here, the surface of the steel, it forms a microstructure which we call martensite, and then it after that, so only what the quenching is done only for 1 second. After that, the steel is allowed to there is no more quenching happening. So the heat from the center radiates outward and then slowly temper the surface again. So we call it tempered martensite. And so at the end, you have a steel rebar something like this, and I'll show more clear. Here you can see this outer region is tempered martensite, and the inner core is the ferrite perlite microstructure, because the rate of cooling of these two locations are different. So this outer surface is because of quenching, it's getting cooled very fast, whereas the inside surface, it slowly cools. So because of that difference in the rate of cooling, you get two different phases or two different microstructure, but the chemical composition is same. And because of this two different microstructure, you get different properties. The tempered martensite is mainly contributing to the high tensile strength, and it's very hard. So you have a hard surface and you have a ductile core. So this is more ductile, because today if you are going for seismic design, you need a rebar which is ductile in nature. So you go something like this. So you have a ductile core and a hard surface or periphery. Now ideally speaking, if a rebar is very good, you should get something like this or something like this when you actually do this test and look at the cross section of the rebar. I am not getting into how do we do this test, but there is a simple way. You just put some acid which is called nitrile, and then you can actually check how this is formed. And then if you have a poor quality rebar, then you will see that the cross section, when you look at it, will be one of these type. Either you can see here it's kind of eccentric, there is this over here, there is no martensite, there is no martensite here. If you look here, there is no martensite. If you look here, there is no martensite. So this actually, in this case of rebar, for example, both the inner, this core region and this is actually exposed. So you have a region where it is highly vulnerable to corrosion, potentially vulnerable to corrosion. So when we look at steel rebars, we should look for, if you're looking for TMT or QST rebars, we should look for a bar which has a very good tempered martensite ring. Ring means full ring should be there, discontinuity should not be there, a continuous phase of tempered martensite. That's what we are looking for. Now other type of steel, one is galvanized steel rebar. So steel can be protected by zinc coating. So you provide a very thin coating of zinc on this rebar, and it is not like you are actually painting. To be precise, we call it hot dipped galvanized rebar. In other words, there will be a hot zinc bath into which you actually dip the steel rebar and then take it out. So there is a proper fusion bonding between the zinc and there is a proper bonding between the zinc and the steel, and the steel surface should be very clean. So it's a manufacturing process itself is quality control must be ensured at that time, and then it forms a very stable corrosion product which is actually protecting the further steel from corrosion. And the corrosion products are loose, powdery minerals that are less volatile. So like in the case of steel, we said that the rust is actually going to create expansive forces, which does not happen in this case, and so there is no cracking happening. Now one advantage of using the zinc is that you are actually increasing the chloride threshold of the steel rebar or the rebar system which has the zinc coating. The moment you put the zinc coating, now you need more chlorides for the rebar to start corroding. So that's one advantage of this. So in other words, it is, you are increasing the chloride threshold by 2 to 4 times. Okay. Now also zinc has a very wider passivation range, or in other words, for a wide range of pH the zinc will not corrode. In the case of regular steel, if the pH drops to about 9 or sometimes we even say about 11, if it is below 9, it will, steel will definitely start corroding. So in the case of pH you can have a wider range and it will not corrode. And even for as a third case, even if it is corroding, the rate will be less. So there are definitely advantages of using zinc coated rebar for enhancing the life or getting better durability, things like that. This is a example bridge where galvanized rebar is used. This is a temple structure where the galvanized steel rebar is used. Okay, when we build temples, we want it to last for, not just 50, 100 years, we want to last for several centuries. So hopefully this will last like that. Now other type of steel or the coated reinforcement is the fusion bonded epoxy coated rebar. Most often we see that people only call like epoxy coated rebar. Ideally speaking, we should call fusion bonded epoxy coated rebar, where these bars are, or this epoxy coating is supposed to protect the rebar. I very precisely said supposed to, because what happens is most of the time we see that it does not protect because of mishandling at the construction site. We induce some cracks or scratches on these rebars because you put this rebar on the site and then drag it on the site, which lead to scratching along these ribs, it will scratch. So that can happen. And if there is a scratch, imagine this is a scratch here. If there is a scratch, what will happen is moisture can actually go into that scratched location, and then you can actually have crevice type of corrosion under the epoxy, or we also call it under film corrosion. Basically the idea in using epoxy, the idea was to protect the steel from corroding, but what we are seeing is if it is not handled properly at site, if the epoxy coating is not really good, it can actually affect the, it can actually make it more vulnerable to corrosion. Okay. Now this is some example from of the epoxy coated rebars or fusion bonded epoxy coated rebars which were used on some construction site. You can see that this person is actually bending this bar, and at that bend you can see significant amount of cracking happening. This is because the epoxy was not elastic enough, so it went to, it cracked upon bending, and they even tried to put some epoxy on site just to cover up this cracked epoxy, but it doesn't really work. So my point, or my opinion here is that unless we are really able to produce quality epoxy coating, which means crack resistant epoxy coating, and enhance the handling, or consider it as a very delicate piece on site, we should not be using the epoxy coated rebars. So you can very clearly see here on these bars there is corrosion starting, brown stain, you can see already it started rusting. Now if this rusting going on, it's going to continue like this, and then it will create a lot more corrosion in short period of time. When we say short period of time, I am even talking even couple of years only. Okay. And this is an example bridge from this picture was taken about 5 years after the construction of this bridge, where you can see very clearly here a significant amount of rust. Somewhere here and there you can see some epoxy coating, but there is a significant amount of rust just in 5 years. and here you can again see a lot of rust actually happening along the ribs. So definitely very clearly we know that unless the bars are handled properly at site and the epoxy coating is scratch free or damage free, and if it is not elastic enough, these are the reasons by which it can lead to corrosion. So the takeaway here is it's more dangerous to use a damaged epoxy coated steel than unconventional uncoated steel. The point is, if you did not have epoxy coating here, you wouldn't have this localized corrosion happening, or there is no chance of underfilm corrosion. So it's very prone to corrosion when you have a damaged epoxy coated bar. Now we talked about different type of steel. So if you look at the comparison between these steel cost comparison, if you think that the conventional steel, if your cost is 1 unit, and the epoxy coated steel you can expect about 30% more you will have to invest, and if it is galvanized steel it will cost you almost double, and if it is stainless steel rebar 6 to 7 times more expensive than the regular steel. And if it is, there is another way I didn't cover this earlier, stainless steel clad rebar, where what it means is a regular steel with couple of millimeter thick layer on the top, just a cladding on the rebar. So 1 or 2 mm cladding you will see, and that is supposed to protect the steel from corroding. So that is also costing about 2.5 times more than the regular steel. So you have to weigh in depending on what type of structure you are building, how long you want the design, how durable you want the structure to be, and how well how well you will be able to take care of the steel at the construction site, means proper handling, etc., quality control. Then you can decide which type of steel you can go for. And note that this cost difference is in 1999, and I got this from not based on an Indian document. So you have to really see cost differences for the scenario which you are in. And this is a corrosion resistant steel, like a stainless steel, usage of stainless steel in a bridge in New Jersey. You can see here stainless steel is being used. Means why I'm showing this picture is there are places where a regular steel will not be sufficient to build a maintenance free bridge. So if your bridge is very important bridge, maybe you will have to go for stainless steel. But in India I think it's not really a scenario. In a very cold climate where they actually put a lot of de-icing salt, the corrosive environment is much severe. So in such cases they are actually forced to use this stainless steel rebar. And this is another bridge in Toronto, Canada. Again stainless steel rebar is used. Very cold climate and lot of application of this chloride salts. So that's why they are forced to use this sometimes. Now in India we are now going on, we are constructing a lot of pre-stressed concrete structures, all these flyovers, metro construction, high-rise buildings, the slabs in the high-rise buildings, they are all, we are using this post-tension systems, and different type of strands are available. So you can see this is a 3-wire strand, 1 wire, 2nd wire, 3rd wire. This is a 7-wire strand. There is 1 wire at the center which is a straight line, straight piece, and then you have 6 outer wires. So we call the center one king wire and the outer one outer wires. So the 7-wire strand and a 3-wire strand. So the 3-wire strand is widely used in the construction of railway sleepers, and these are mainly used in the construction of buildings and bridges. So there are some way of protecting these strands is like there is a mono strand, we call it. It's a sheath strand. You can see there is a grease coating here. So in between the strand and this plastic sheathing you have grease, and this grease is supposed to protect the strand from corrosion. And this is another coated strand. I don't think this is available in India yet, but there are strands which are epoxy coated, made of epoxy coated wires, again 7 wire. center king wire and then the 6 outer wires, when this is epoxy coated wire. So but again, and because you remember these strands are used by stretching them, or you are pre-stressing, so you stretch these strands. So if you don't have good quality epoxy coating, the epoxy coating itself might scratch or might crack. So that should be very well taken care before actually trying to use some of these products. And this is how the strands are being made available to the site, because most of these strands we use in a very long pieces. It's not like a regular rebar, so you have to sometimes go from pillar to pillar. So this is coming in coils. Okay. Now the strands, one mechanism would be stress induced corrosion, and at the same time chloride, carbonation, all that you have to worry about. Now cathodic protection for corrosion prevention. This is a technique which is widely used, especially for cases where you already have an idea that it is going to corrode, and there is no way, no other way to actually protect the structure. And so in such cases we assume that okay, this is going to happen, corrosion is going to happen, so let's do something to protect it from corrosion. What we do, like this is an example which is shown on a buried pipeline, where if we expect that this pipe is going to corrode, what we do is, corrosion is what, in the anodic reaction, if you remember, there is a release of 2 electrons and the Fe2 plus ions, right. So if we can actually prevent that releasing of electrons, that means if 2 electrons are releasing, that is what is meant by corrosion. If I am ready to supply 2 electrons, then the net effect is 0, means there is no corrosion. So that's the whole idea here, is you create another electrical circuit by which you are actually supplying electrons to the metal which needs to be protected. So you are converting the metal which needs to be protected to a cathode by providing a sacrificial anode. So corrosion is now happening between this metal and this metal, means this is corroding in preference to the metal which we need to protect. So that's why we call it sacrificial anode, because this is sacrificing itself so that this cathode or the main pipe is protected. Okay. There is one more way. In here it is an example shown is by putting a sacrificial anode. There is another way, which is by supplying current by putting a power source. Instead of this anode, you put actually a power source, very small current you pass to the pipe itself. Instead of this bag or this sacrificial anode, you will have a power source which will give enough current to, or enough electrons to the metal which need to be protected. So that's two way of cathodic protection. Now this is an example showing the sacrificial anode. You can see here magnesium rod which is connected to the pipe which need to be protected. So if you remember the picture which I showed earlier on galvanic corrosion, the lowermost, it is that blue slide which I am talking about. You can go through that later. The lowermost element in that was magnesium. So that means if magnesium is connected to the steel, magnesium will corrode faster than the steel. So same way what they have done here is magnesium rod is connected to the steel pipe or iron pipe, which by which the iron pipe is protected, and this is the sacrificial anode, or magnesium rod is the sacrificial anode. We also use bags of magnesium instead of a rod. You can see here, this is a magnesium bag, this is a magnesium bag which is connected to the buried pipeline, and this is supposed to protect this pipeline from corroding. Now some other examples where sacrificial anodes are used. This is actually on top of a bridge deck where you can see this repair is happening. Here is the patch repair, and or some portion of the bridge has corroded, so they are replaced the rebar and putting new concrete there. Now what happens normally is when we repair something like this, the corrosion can happen right at this border. Along this border, corrosion can happen. So to prevent that corrosion along this interface, what we do is we connect something like this. Again, it has a zinc disc. Inside this, there is a zinc disc. It is connected to the rebar. So this is a close-up of this location. So these are the zinc discs which you see, and these are connected to these rebars. And what will happen is the zinc disc will corrode and not the rebar. So it will protect the rebar from corrosion. And this is an example of a riser in an offshore platform, offshore structure. You can see this is small, these white pieces over here. These are all sacrificial anodes, which are connected to these steel, steel structures. And this is a close-up where you can see not of this piece but of another element, where you can see that this sacrificial anode is corroding, but not the steel which the anode is protecting. Okay, so this is widely used. And another way of protecting steel from corrosion is by mixing some chemical in the concrete before actually construction, before constructing the or in other words, while you are during the construction itself, we can include some corrosion inhibitors, some chemicals in the concrete, and which is supposed to enhance the chloride threshold of the steel. Okay, so some of the chemical brand names are given here, but mainly they are calcium nitrite, or sometimes you have amines in that. So different chemicals are available, and it is supposed to actually modify the passive film which is available on the steel surface, and so that the chloride threshold is increased. What is chloride threshold? It is the minimum amount of chloride which is required to initiate the corrosion. So let's say case where you have a regular rebar and your regular concrete without any inhibitors. Imagine the chloride threshold for that scenario is 1 unit. Okay. Now if you put the corrosion inhibitors into the concrete, that chloride threshold might be increased. Let's say if it is increasing by 20%, that means it will have an impact on the initiation time, or in other words, now it will take more time for chlorides to build enough chlorides to initiate corrosion at the steel surface. So the higher the chloride threshold, the more time it takes the corrosion to initiate. So this is one way of doing it, but we can do only this we cannot do once the structure is already constructed. So if you are talking about all the existing structures, we cannot do this technique, we cannot apply this technique. So in such cases, what we do is we also have something called migrating corrosion inhibitors, or we can go for cathodic protection like I discussed earlier also. But in addition to cathodic protection, this is another technology available, which is migrating corrosion inhibitors, where as shown in this picture here, this is a roller and you apply this corrosion inhibitors on the surface of the concrete, and it's what we expect is this material which you apply on the surface, it will actually penetrate through the concrete and in vapor phase, and it will reach the steel. And what they see here, it's very clear, when it reaches the steel, it actually stick to the steel surface and then it enhances the corrosion resistance, or it provides more protection against the corrosion. So this is the idea behind migrating corrosion inhibitor. The earlier one which we called, this is as a chemical admixture, means as you mix the concrete, you have to provide this thing like any other admixture. And other method for existing structures was the use of the cathodic protection system. One more technique available is use a chemical admixture, again as which we call pore blockers. Like in concrete cover or concrete, you will have a lot of pores available through which the oxygen, moisture, chloride, carbon dioxide, all these can penetrate. Like in this picture shown here, there is water available at the surface of the concrete, but it is not able to go into this crack and reach the steel because these pores are blocked. the yellow marks are actually blocked. So here if you see, in through this crack water is able to reach here but not able to go further into the crack, and so you are actually blocking the moisture from reaching the steel rebar. Okay. So this is the idea, and once you don't have enough moisture and oxygen, then you cannot really have corrosion happening. So both these are essential for corrosion to happen. In addition, if you have chloride and carbon dioxide, then the chances are higher. Now, given a scenario like you are in a case where somebody wants to test whether corrosion is happening or not. Now we are going in the corrosion monitoring techniques. So when somebody is asking you, okay, I want to know whether there is corrosion happening or not, one way of testing it is you take an electrode and find the electrical potential of the rebar. Okay. So electrical potential, this is the rebar which is embedded in the concrete, and you connect this rebar or connect a reference electrode through a voltmeter connected to the rebar, and once you connect, then you check the potential of this rebar. You can check it. This is a reference electrode, that means its potential is fixed, and what depending on the reading on the voltmeter, we can determine what is the potential of the steel rebar. Now there is an ASTM standard available where we say if the potential is less than 350 millivolts or 0.35 volt, there is 90% chance of corrosion. If the voltage which you measure or the potential which you measure is greater than minus 250 millivolt or 0.25 millivolt, then you have only 10% of corrosion or 90% of no corrosion or 10% of corrosion. And if it is in between these two, then you have to decide based on engineering judgment what is the scenario. Okay. So this is one way of detecting whether there is severe corrosion ongoing or not. Note that this method will only tell you or give you a probabilistic answer on yes no, means whether there is corrosion happening or not, or what is the probability of corrosion. That is all what you will get in this. Now this is some of example pictures which shows that shows the equipment which are available to do this. There are many companies are producing these kind of instruments which can actually this. So this is the reference electrode. He is actually putting this on this concrete wall. There is rebar inside. You can measure what is the potential here, and you can tell where the corrosion is happening. How do you tell that? By making a contour plot, where you see here some region with red color, they have much more negative potential than the other regions, which indicate that those regions are highly vulnerable to corrosion. So the more the negative region, the more the chance of corrosion. That's how we look at it. Okay, and now imagine you have a very long bridge or a very large building where you want to assess these things. You cannot go around and find these points one by one. So there are electrodes which are we call wheel electrodes. You can see these are 4 electrodes here. In this case, again a wheel electrode, but only one wheel. Again, you can just roll it on the surface which you want to measure, and then it will automatically record the potential data, and it can give you a contour plot. Once you get the contour plot of the potential, then you can decide which region is corroding more and which region is corroding less. More negative the potential, the higher the chance of corrosion. Then another method is to our requirement. Like I said, in the potential you will only be able to tell yes no answer, but what you really need when you talk about service life is what is the rate of corrosion. So to get the rate of corrosion, there is a technique called guard ring electrode technique, where we actually put the reference electrode again connected to the rebar, and this is the guard ring or reference electrode here. You can see the reference electrode put on a concrete surface, and to the other terminal of the equipment it is connected to the rebar inside. Okay, and then this will give you the rate of corrosion. What we do here is we isolate this region and then measure the rate of corrosion in that region. So that's how we check. Now rate of corrosion, once you know the rate of corrosion, you can determine how much loss of the rebar will happen in X number of years or N number of years. So if you say that you have a safety factor, okay, I can afford to lose 10% of the steel, assume like that, then if you know the rate of corrosion, you can calculate how many years it will take to lose 10% of the steel. So if you say 5 years, if it takes to lose 10% of the steel, then I can plan accordingly to generate money to do a repair work in 5 years. Because budgeting is also very important. You cannot just say, okay, today I found it is going to corrode, tomorrow I need to repair it. It may not be possible all the time. So what you really need is a time. So you need to be able to do these tests ahead of time, so that you get enough time to plan your repair and maintenance activities. Okay, or in other words, if you know that corrosion is happening, you can also go for cathodic protection or some way of controlling the corrosion, so that the rate of corrosion is significantly reduced and you can have durable structure. So we'll get into the summary slide, where what we covered. First we said that in general high pH, concrete has a high pH, and because of which we are able to protect the steel, or steel is very well protected in high pH, and fresh concrete has a high pH. So but when the concrete starts getting carbonated, the pH level drops, and once the pH is below 9, it can actually start corrosion. And in the other case, if it's a chloride is reaching, even without the reduction of pH, you can still have corrosion if the chloride level at the steel surface is above the chloride threshold. And we looked at different ways of either coating the rebar, or with metallic coating, or using a chemical in the concrete, so that we can increase the chloride threshold of the system, and by which we can then increase the service life. And then we also mentioned that moisture and oxygen are essential for corrosion to occur, and if chlorides and carbon dioxide are present, then the chances of corrosion are higher. But anyway, point is moisture and oxygen are essential. If you can prevent the structure from moisture or oxygen, then you can stop corrosion, but it is practically impossible to achieve that. And corrosion inhibitors can be used to prevent corrosion. We looked at different type of inhibitors. We looked at the admixture, which can be used when you are talking about new structures. Also we looked at migrating corrosion inhibitor, which can be applied on an existing structure to prevent corrosion. And we also looked at the cathodic protection systems to reduce the rate of corrosion, so that the life can be enhanced. And then we also looked at how to monitor the corrosion. First one we looked at is the probability, how to find what is the probability of corrosion occurrence with an equipment by measuring the electrical potential. And then we also looked at how to get the rate of the corrosion using the guard ring electrode and the linear polarization resistance techniques. And once you know the rate, the advantage is you can actually plan for maintenance and repair activities, and also probably do some retrofitting action, like or do some repair strategy, so that your life of the structure can be enhanced. I think that's it for part 1. In the part 2, we will look at more on the deterioration mechanisms in the concrete, or rather to be precise, we will not look at the steel part, we will look at the cover concrete, what happens to the cover concrete, and how to actually in the part 3 we will look at how we will be able to design a concrete structure so that the durability can be enhanced. Thank you. Now we will go see if there are any questions to be answered. Welcome back. We'll just go through some of these questions which we got. First question, what are the favorable conditions that loses its ions? I did not really understand the question. If you can rephrase that question and then type it again, I'll try to answer. Be precise in what you're asking. And then what are next question? What are some tests to find chloride permeability in concrete? There are multiple ways by which we do. One of the tests is RCPT, it's widely known as rapid chloride penetration test, or it's sometimes even called as rapid chloride permeability test, where we actually take a concrete cylinder and then apply, put the concrete cylinder in on one side of that it will be chloride solution, and then applied some current, and then we can check how deep the chloride has penetrated into the concrete, and then you can look at the obtain the permeability values for comparative purpose. Anyway, we will cover this test in the part 3 of this course. And then next question is, can we lower the rate of corrosion by using any specific cement? Also describe the role of fly ash in corrosion control. Yes, we can definitely lower the rate of corrosion by using a cementitious system which has high electrical resistance. So if you use fly ash, or if you use most of the pozzolanic materials, what we have found is the electrical resistivity of the system is significantly enhanced. Once the electrical resistivity is enhanced, that means the rate of corrosion will be lower, okay, in general. So in fly ash concrete, yes, we can really control the rate of corrosion. Also, the most of the case what we are seeing is fly ash reduces the penetration of chlorides, so it will in an effect it will take much more time for corrosion to initiate and propagate. Mostly what we see is iron hydroxide as the rust product, but if you remember, sometimes when you look at the rust, you might see the initial rust is brownish in color, and then as time passes it gets more and more oxidized, it becomes greenish, dark, almost black in colors, which is highly oxidized rust. So if you have more doubt, you can put another question. The next question, in a pipeline, the sacrificial anode prevention method, up to what range of length it would be effective? Mostly the sacrificial anode method is not effective for long distance. If you are talking about a sacrificial anode, maybe you are talking about in terms of meters, but if you are talking about ICCP system, which is impressed current cathodic protection, there are a technology available whereby which you can even go for one system, like several kilometers we can actually control the corrosion. Systems are available. The next question is, calcium hydroxide causes increases of ITZ thickness. We need to reduce the calcium hydroxide content to avoid leaching. How does it affect the total strength of the RCC structure? I mean, this leaching, if you are talking about strength, it's mostly governed by the calcium silicate hydrate. So this calcium hydroxide leaching, it affects mainly the pH of the concrete, and which in turn might affect the corrosion. But the strength, when we talk about it, mostly CSH gel, which we are more interested in, or mostly the governing factor, if it's only leaching of calcium hydroxide. But then once the calcium hydroxide is leached out, then the problem is you will have more space available in the concrete, so which might indirectly influence the strength also. But mostly this leaching is a phenomenon which is near the surface, so it may not be a concern for the strength of the overall structural system. Now, what are the initiating factors for depassivation? like we discussed, availability of moisture, availability of oxygen, availability of chlorides and availability of carbon dioxide at the steel surface can definitely influence the corrosion or depassivation. Among these four, moisture and oxygen are essential for corrosion to occur. Other factors actually accelerate the corrosion. How can the migration admixtures travel to the site of corrosion in the reinforced concrete? Yes, so these migrating corrosion inhibitors, they actually travel through the pores in the concrete towards the steel, and once it travels through the pores, reaches the steel, it actually get deposited on the steel surface and stops the corrosion. So it's so small, so these migrating corrosion inhibitors have a vapor phase. So these vapors can actually penetrate through the micropores in the concrete. So there are two questions remaining, one on the favorable conditions iron loses its ions, and the other one is morphology of corrosion in the active state. If you have further clarification required, you can put the question again with more specifics on that. How is the pore blockers applied at site? Next question is, how is the pore blockers applied at site? Pore blockers are actually like an admixture. It is mixed with the concrete. We do not normally apply it on a new it's only for the new structures, means it's as an admixture. So how can we increase the pH? There are methods which called realkalization technique. You can look at it on the other sources, where we apply current again, and you drag more hydroxide ion to inside the concrete. So you make a bath outside the concrete surface which is rich in hydroxide ion, and then apply the current, so that these hydroxide ions are driven to inside the concrete. So you eventually you will get the higher pH. The term is realkalization. You can look for that. Next question, how is the repairment of corroded reinforced bars done? There are a lot of things to talk about that. So I don't know if I can cover how is it repairment of corroded. So one way of doing it is, you clean the rebar, remove all the existing rust, and then apply some anti-corrosive agents which will sometimes have zinc in it, and then again cover the concrete with new cover material, new cover concrete. I think this is the simplest way of answering that now, of how corroded reinforcement bars are done. So clean the rebar, proper surface treatment, apply an anti-corrosive agent. There are different ways, or use a very good concrete cover as a repair material, and then cover the corroded bar again.
But does the deformed bar increase the ductility of bar as compared to normal or plain bar?
Ductility is a function of the microstructure of the steel. Okay, so are you talking about cold twisted deformed bars?
The normal deformed bar.
Yeah, the normal deformed bar which is available today, which we call TMT. So that deformations are done mainly for the bond. The ribs you are talking, right?
Yes, sir.
Yeah. So ductility is a function of microstructure. If you are talking about cold form deformed, that is a cold twisted deformed CTD bar, there you might have lower ductility compared to the currently available TMT bars. Like I mentioned, in the TMT bar, you have a ductile core and a highly hard tempered martensite cover, right?
Yes, sir.
Yeah, did I answer your question?
Okay, sir. Thank you very much.
Okay, so one recent question, why TMT bars are mostly used in India? I mean, recently I found that actually TMT bars are, it's not that only in India we are using it. It's used in Europe also heavily, But one thing which I found is the quality is very good. At that martensite ring which we were talking, it's fully available on those bars, but many of the bars which are locally made, we don't see this proper rings, so you should be careful. Now coming to the question why it is mostly used in India is because I think this was probably a cost effective approach in enhancing the ductility and at the same time getting good corrosion resistance. So I think that may be the reason. I don't know what more to tell about it. But for example, in the US, you don't get TMT rebars. You get full microstructure will be of similar type. Like there is no ring like that. But in India, it is used. I think it is widely used because probably when you tell to change the with the same manufacturing units with slight modifications, maybe they were able to make TMT bars using old machinery and steel. I don't know more than that. Okay, thank you.